Think about the rhythm of a standard exam. Read the prompt, pick the bubble, fill it in, move to the next. 60 questions, 60 minutes. We have built an entire educational infrastructure around a specific assumption that rapid recall and rote accuracy are the ultimate proof of intellectual mastery. But this emphasis on speed introduces a functional disconnect when we look at the evolutionary biology of how we actually think. Look at this diagram of the brain's neurobiological architecture. The area glowing in green is the prefrontal cortex, the biological engine of higher-order intelligence. This region coordinates advanced cognitive processes, integrating incoming data across the brain to formulate complex thoughts. While the prefrontal cortex is built to navigate ambiguity and solve multifaceted problems, its resources are bypassed when the task is reduced to rapid-fire data retrieval. Yet a typical exam structure demands exactly that. It forces the brain to act like a simple lookup table, matching a prompt to a predefined output as quickly as possible. If we want to measure true understanding, our assessment architecture has to change. We must align our tests with the neurobiology of the human brain. When students fail to apply what they have learned in the real world, it rarely means they lack intelligence. It means the assessment failed to engage their cognitive machinery. To understand where the disconnect happens, we have to look at the brain's baseline storage systems, starting with episodic memory. Episodic memory stores isolated facts and specific events. It is useful for immediate recall, but it has a built-in biological flaw. It is highly susceptible to rapid forgetting. Because it yields quick, easily measurable answers, traditional testing relies almost exclusively on this highly fragile system. True learning, however, happens in the brain's superior storage counterpart, semantic memory. This system stores long-term abstract concepts. It holds the underlying, interlocking rules of how things actually work. These two distinct memory types directly dictate how the brain computes decisions, specifically, whether it relies on rigid logic or human adaptability. An algorithmic approach demands a straight, linear path from a problem to a single correct answer. That computation is straightforward, but biologically unnatural for complex thought. The human brain prefers adaptive decision-making. It wants to navigate branching, complex, and ambiguous paths to discover novel solutions. Any test that solely measures episodic recall and strict algorithmic logic is completely missing the higher-order intelligence that makes human cognition so powerful. We can map those underlying memory substrates directly to the way a student thinks during an exam. When an assessment relies on isolated episodic memory, it produces convergent thinking. This diagram compares the two primary thinking types and illustrates exactly how their cognitive outputs differ. The top pathway maps convergent thinking. Notice how the inputs representing knowledge, understanding, and application all collapse down into a single restrictive target point. This represents the search for one correct answer through simple associative recall. It proves base-level application, but it falls short of proving true mastery. Mastery is demonstrated through divergent thinking, which is the cognitive output of a well-developed semantic memory network. Follow the diagram down to the divergent pathway. Here, a single starting prompt branches outward into multiple, varied clusters, representing analysis, evaluation, and creation. That outward branching action, searching for multiple solutions and developing new neural connections, is the actual mechanism that drives complex idea generation. There is an obvious administrative reason we avoid testing this way. Convergent thinking is incredibly cheap and easy to grade at scale. Divergent thinking is messy. It is complex, nuanced, and inherently subjective to evaluate. Prioritizing that administrative convenience over biological reality gives us an illusion of learning, one that collapses the moment a student faces a real-world problem without a multiple-choice grid. There is another major logistical constraint embedded in modern assessment that actively works against the brain: the strict time limit. Rote associative recall requires very little computational power. Retrieving a memorized fact from episodic memory happens almost instantly, but true cognition hits a biological bottleneck. This section of the chart breaks down the importance of the time factor. The fast clock on the left illustrates automatic reactions. The hourglass and the slower clock on the right represent the reality of solving complex tasks. The neurobiological reality is straightforward. Coordinating divergent thought and engaging the prefrontal cortex for deep semantic processing physically requires more time to synthesize connections. By enforcing extreme speed constraints, standard tests actively penalize deep comprehension while falsely rewarding superficial memorization. So, knowing this neurobiological diagnosis, how do educational designers architect a system that actually measures intellect? The framework requires 3 practical shifts. Rule 1. Assessments must prioritize open questions over closed selections. Open questions force the brain out of its episodic lookup table. Formulating an individual answer directly triggers the divergent, higher-order mechanisms of the prefrontal cortex. Rule 2. Tests must prioritize contextual recognition over basic associative recall. We shouldn't ask students to simply regurgitate a definition floating in isolation. Forcing a student to recognize and apply a concept embedded within a messy, realistic scenario provides tangible proof of true semantic integration. Finally, Rule 3. The time horizon must be extended to match cognitive biology. Removing artificial speed pressure is not a matter of lowering academic standards. It is about allowing the prefrontal cortex the necessary biological time to compute an answer. These 3 shifts take evaluation away from being a mere administrative sorting mechanism and turn it into a rigorous metric of intellectual capability. Building an effective assessment requires aligning the structure of the evaluation with the fundamental biology of the human brain.